So another important topic is the determination of and naming of directions or points or planes within the crystal structures, the crystal lattices that we introduced in the previous lectures. So this goal of defining directions and planes within a crystal to be able to discuss properties of the crystal or determine properties of the crystal is done via a system called the Miller system of indices, or shortly Miller indices. So what this does is that it allows us to be able to identify points, directions, or planes, meaning make identifications in 0 dimensions, 1 dimension, or 2 dimensions within a unit cell of a given crystal. So to, for example, discuss the difference between an atom at the corner of the unit cell or at the center of the unit cell, you could use terms like corner or center, but you could also use some numbers, some indices, to identify, to distinguish between these two atoms. Similarly, to distinguish between two different corner atoms, instead of saying the left top corner or the right top back corner, you can use numbers that identify these positions. That would be a point. The position of an atom would be a point. The line or the direction moving from one atom to another, so through a sequence of atoms, would be a direction, and a two-dimensional version of that would be a plane of atoms. So then you might say, why is this important? And as one example, planes are of particular importance in crystals because they influence where it is easy, they indicate where it is easy or where it is difficult for fracture or failure to happen. So without knowing anything about the strengths of the bonds, you could estimate the ways in which a single crystal could fracture. So as an example of this, you can think of a stack of papers. So a stack of papers is kind of like a crystal structure in that there is some repeating structure. And you may imagine that one stack, one piece of paper among the stack represents one plane of atoms in 2 dimension. And so then when you consider that the stack, the individual pieces of paper are full of more atoms and that are bonded more strongly to each other than the atoms bonded between adjacent pieces of paper, you can observe and link that to the fact that a stack of papers will be easiest to deform or to separate the atoms of by pulling or pushing the pieces of paper parallel to each other. So when you try to, instead of sliding the pieces of paper parallel to each other, when you do try to change the positions of the atoms with respect to their neighbors in any other direction, for example, perpendicular to the stack, the resistance is significantly greater. So a stack of papers is a solid with stronger, maybe shorter bonds and stronger bonds along the pieces of paper, along those planes. And if you can identify that these planes are the strongest, then you can imagine that instead of perpendicular to them, being parallel to them, pushing or pulling the planes with respect to their neighboring planes is the simple way of deforming or breaking this structure. So the concept of directions here is shown in this image, where you have two different directions shown. It's a two-dimensional representation of a crystal, so it's kind of simplified, but you see that here you have one direction going from here to here, another direction going from here to here. So in a direction, the way in which you're moving is important along the line. So if you look at the number of atoms in this direction per a given length, you see that you have 5 atoms along 4 distances. And here in this direction, you have 4 atoms along a similar distance, in fact, a greater distance. So here, if you just focus on maybe from this point to this point, this is equivalent to the side length of this square, whereas this is the diagonal, hence it's square root of 2 times, almost 1.4 times greater in length, but the same number of atoms. So you can imagine that along this direction, there are fewer atoms per length unit, per unit length, than along this direction, indicating that they must have different properties along, the crystal must have different properties along these 2 directions. Hence, for reasons as such, it is important to be able to identify directions, points, and planes, and this is done with Miller indices. So to start with the 0-dimensional version, points, the position of any point located within a unit cell is specified in terms of its coordinates as fractional multiples of the unit cell edge lengths. The unit cell edge lengths are A, B, and C. So this distance along the x-axis is A, this is B, and this is C. And note that A, B, and C are equal for a cubic unit cell, but for different unit cells, they might not necessarily be equal. And the position is defined as a multiple, fractional multiple, meaning from 0 to 1, of the unit cell edge lengths. And hence, for the point P chosen here, we have the coordinates Q, R, and S, and the value of Q is, what Q does is it defines as a fraction how far you are from the origin along the x-axis length. So if Q, R, and S are all equal to 1, Q times A, the distance along the x-axis, is equal to A, and Q times R times B and S times C are also 1, and that would indicate this point here. This point here would be QRS, where Q, R, and S represent are all equal to 1. Now, this point here would have a value of Q as 1, a multiple of the side length A value of R equals 1, and a value of S equals 0, because there is no, this position doesn't have your at Z equals 0. So then this point would have the indices 1, 1, 1. This point would have the indices 1, 1, 0. This point would have the indices 0, 1, 1. And this point would have the indices 0, 0, 0, because it's the origin. This point would have the indices 1, 0, 0, because both along the y and the z axes, there is no, there has been no movement from the origin. So you get the point. Now, directions are one-dimensional, hence they use a line between 2 points or a vector. And there is a rule that's followed, and it'll make more sense when we follow the example given on the next slide. But a vector of a convenient suitable length is positioned such that it passes through the origin of the coordinate system. And so to define the direction between 2 chosen points, So the question might be, give me the name of the direction from this point to this point across the body diagonal. So from this point to this point, you draw a vector that goes from that point to the other, and then you check that it passes through the origin. So in that case, it does pass through the origin. The length of the vector projected onto each axis is determined in terms of unit cell dimensions, again, A, B, and C. So again, with using values of 0 and 1, using multiples, using values between 0 and 1, then these three numbers that define that are the coefficients of A, B, and C are multiplied or divided so that a smallest set of integers can be obtained. And these numbers are enclosed in brackets or square parentheses to when they're being shown, to indicate that what's being shown, the numbers indicate a crystal direction, hence a vector between 2 points. The U, V, and W correspond to the reduced projections along X, Y, and Z, respectively. So as an example, we have a vector shown going from the origin to this point here, and the vector drawn passes through the origin of the coordinate system. Hence, this is sufficient. We'll see what translation of the vector means in another slide. So then projection of this vector along X, Y, and Z shows that along X, the distance is A over 2, or it is 1 over 2 times A, where the multiple is 1 over 2, and the side length is A. Along B, it is 1 times B, and along C, it is 0 because this is in the XY plane. So you see that it's the multiples or the projection onto X, Y, Z show that the numbers of interest are 1 over 2, 1, and 0. So reducing these numbers to the lowest set of integers, the smallest set of integers, is done by multiplying this by 2, because this needs to become an integer by multiplication with 2. This also gets multiplied by 2, and this gets multiplied by 2. So this gives the new indices of 1, 2, and 0. Notice that this corresponds to the identification, the projection along the x-axis, this along the y, and this along the z-axis. And then, because these are the smallest set of integers, they're all integers, we put them in brackets and we say that this direction, or this line, this vector, is defined as the 1, 2, 0 direction. Now you might wonder, you might ask whether this is identical to the direction of the direction in the opposite direction. So going from this point within the unit cell to this point, it seems like it would be the same, but it would not be, because the projection along the x and y axes would be negative, meaning one would be going in the negative x and the negative y directions. So the z-axis portion would remain 0, but the values of 1 and 2 would become -1 and -2 to indicate the difference between this vector going in this direction and the opposite vector going in this direction. So then this shows some other examples, and you see examples of some negatives here. So here you see that the crystal directions A, B, and C, or the vectors that represent them within the unit cell, are shown. Notice that a direction is actually one-dimensionally infinite, meaning it is not bound by the unit cell, but we show, to be able to define it and name it, we show a vector that is within the unit cell, hence choose the points on the edges or corners of the unit cell. So the vector A, this one here, is what we had seen earlier, what I described earlier verbally, goes from the origin to this point, and this point is 1 times A, 1 times B, and 1 times C away from the origin, or in this case, because it's a cube, all 3 sides have been labeled A, hence it's 1A, 1B, and 1C away. So we write that as such, then we invert the 1, 1, and 1, and we again get 1. So this is the 1, 1, 1, the direction. So then vector B moves along the positive y-axis, but it moves along the negative x-axis, and it does not move along the z-axis. So vector B, in fact, is shown here to be incorrect. So there has been a problem, obviously, with the placement of this funny little dash or funny little line placed above the number to indicate that it is negative rather than putting it in front of it. This is the notation preferred for whatever reason. And this should actually show that the line here should be in front of, on top of the first index. So we can fix this as such. So then the vector C, so this moves 1 times A in the negative x direction, so minus 1 times A, 1 times A in the y direction, and no movement along the z direction, the axis. So for vector C, you see that there is movement along the x, y, and z axes. In the z axis, it is negative because it's moving along the negative z axis. And along y and x, it is moving in the positive sense. It is 1 times A, 1 times A, and minus 1 times A. And that gives you 1, 1, minus 1. Minus 1 again indicated as such. So this one is correct. This one was incorrect. And we fixed it. And in some crystal structures, several directions that are not parallel to each other, that have different indices, may actually have equivalence among them. So they might have spacings of atoms along these directions that are actually the same. So examples of these in cubic crystals, like the one that we just saw where A, B, and C are all equal to each other, you identify the different directions and you label all of them, or you group all of them into a so-called family. And to indicate that this is a family being represented, you use these angle brackets. So this here, with angle brackets, means it is the family of directions within a unit cell, which all have equivalent properties. And this here, with 1, 0, 0 in square brackets, indicates that this is the actual 1, 0, 0 direction. So looking here at what the 1, 0, 0 direction is, that indicates positive movement along the x-axis, 0 movement along the y-axis, and 0 movement along the z-axis. So it means the vector from the origin to this point here. So this length in this direction is the direction that's described by 1, 0, 0. So you notice that for a cubic crystal, if it is simple cubic, it would have, for any case, simple, face, body, whatever, it would have a corner atom here and a corner atom here. And if it were a face-centered atom, along this axis, it would have no other atoms. And if it were a body-centered atom, along this axis, it would not have any other atoms. And if it were simple, it would not have any other atoms. So in all cases, this side length from this point to this point here would always have two vectors, two atoms, one on each end, one at this corner and one at this corner. Similarly, here and here, you would have two atoms, and this length, this length or this direction would have the same properties. Similarly, the movement from this point to this point here would have two corner atoms along a length of A, hence it would have equivalent properties to the direction described earlier. So the 1, 0, 0 direction and the 0, 0, 1 direction and the 0, 1, 0 direction all have the same properties. So now we see that 1, 0, 0, 0, 1, 0, and 0, 0, 1 all have the same properties. And similarly, they're negatives. So the same side of the same edge of the cubic crystal, but moving along the opposite direction. So instead of the positive x direction, moving along negative x along this edge of the unit cell would also have the same properties. Hence, you get 6 different directions within the unit cell that are identical. Now, if you look at whether B and C are identical, you see that C and B are not identical because they have different lengths along which they're described. Along those directions, the length of the unit cell is different, and depending on the type of unit cell configuration you have, the number of atoms may also be different. But you might imagine that from this point to this point, and from this point to this point, you will again have identical properties. However, they will differ from the properties of 1, 0, 0 or 0, 0, 1. So that will be a different family of directions. So to repeat, the diagonals here or here, the diagonals of the back face or the diagonals of the front face will all be members of the same family of directions. So then, for some cases, in some cases, it may be useful. We'll see examples of these when you see the problem, the study questions or the problems shared with you. In some cases, it may be necessary to be able to describe the angle between two different directions. So what that means is, for example, here, the angle between the plane, the direction A, or the vector A, and the vector C is possible to figure out using common sense and using a little geometry. Now, however, if I ask you the direction, the angle between the two directions B and A, so some sort of angle between them, this would be tricky to do because it's not, so any angle between two vectors within the unit cell that is not 90 or 45 or something special is going to be difficult to calculate. So to do this, a method that will come in handy will be the cosine product or the scalar product, which will be where A and B are two vectors, which will be described by this formula, as you've seen in earlier math classes. So then when you have indices, H1, K1, and L1 describing the direction A, and indices H2, K2, L2 describing the direction B, so the two directions A and B, or the two vectors A and B, the angle between them will be, okay, this should also be corrected. So let's correct that as we go along. The angle between them is described here as alpha. So if this angle is alpha, then this formula holds, and it means that cosine alpha, again from earlier math courses, we're not deriving this relationship, but we're just using it here, is possible to calculate by this formula here. So it's by multiplying the first two indices corresponding to the movement along the x-axis, plus the two indices for the y-axis, or the y-axis direction, and the two indices along the z-axis direction, and dividing it by this square root, one can obtain a value for alpha that describes the angle. So you might imagine that a simple case shown here would be, say, the angle between this vector, which would be the 0, 1, 0 vector, and this vector here, the 1, 0, 0 vector. So if this is 1, 0, 0, and this is 0, 1, 0, this would have a value of 0, this would have a value of 0, this would have a value of 0. The denominator would be non-zero, but the numerator would be 0, and the value of alpha that corresponds to cosine alpha equals 0 would be 90 degrees, as this angle here is 90 degrees. The same would hold for this angle here, because this is 0, 1, 0, and this vector here is 0, 0, 1. So you would get 90 degrees for alpha. However, if you chose some other vector, you could end up with a non-zero numerator, and hence a value of alpha that's different than 90. So this scalar product is useful for determining the angle between two vectors, and in our case, two different crystal directions. So directions are in one dimension. Planes of atoms are two-dimensional. And as I said, the orientations of certain planes may be important, such as in the case of a stack of papers. When you discuss the plane of atoms within one piece of paper, or you discuss a plane of atoms perpendicular to this stack of papers, they will have a different number of atoms along a different spacing of atoms within that plane. So then, again, it may be important to describe the differences using a simplified method, and the Miller indices, given within soft parentheses or regular parentheses, 3 indices describe every single direction, every single plane, within a crystal, within any crystal that you can choose, except a very special type of crystals called the hexagonal crystal system that we can ignore for this class. So except a very small portion of actual materials, almost all materials are possible to describe the planes of using 3 indices. Now, in the case of this particular type of crystal system, the materials that follow this rule there will be a need mathematically for a 4th index, but that's not of great importance here. So for everything else, for most every crystal, 3 indices describe everything. And one other statement here that we'll describe in the following slides graphically is that when you have planes that are parallel, they have equivalent or identical indices. So they will have essentially the same name if they are parallel. We'll show why this is the case in this slide. So then, first, let's see the formal procedure for determining the indices of a plane, and then we show an example and everything falls into place. So the rules, why do we follow these man-made rules? Because this is a method and it works, and it is a simple method that is robust and that it does not fail when you choose a new crystal and a different crystal. It always works. So you look at the plane of interest that is being asked, that you want to know the indices of, the name of, and you look whether this plane passes through the selected origin. So if it does, this causes a problem, and the plane must be shifted with respect to the chosen origin so a parallel plane must be chosen, or the origin must be shifted, which is the same thing. So the plane chosen being used must not pass through the origin. So this will make sense in a slide or two. When this first rule is satisfied, then the plane, the crystal plane, either intersects or parallels each of the three axes. So it might cut through X, Y, and Z and have an intercept, or it might cut through two of them and have one intercept, or it might cut through one of them and have one intercept and be parallel to the others. So the length of the planar intercept for each axis, again, along the X, Y, and Z are determined in terms of the parameters A, B, and C, the lengths of the unit cell, the lattice parameters. Then the reciprocals of the numbers used to determine the length along the axes, these so-called multipliers, are taken. Then, if necessary, there's an adjustment of the numbers so that the smallest set of integers is obtained by dividing or multiplying by a common factor. And then the indices are obtained, and they're represented within soft parentheses for distinguishing between directions and planes. So we see our example. The example here is, it's not shaded, but it is this plane. So it's the plane that goes from this point to this point, and this point. So notice again that the idea, or know that a plane is two-dimensional, so it keeps continuing in this direction or in this direction, but we're here only interested in the portion, identifying the portion within a unit cell to be able to name it. We see that the plane passes through the selected origin O, so a new origin must be selected, or the plane must be translated to get rid of this problem, to satisfy rule number one. So this can be done as shown here. This was the original origin, shown it with O, X, Y, and Z directions. If you translate the origin one unit cell length, side length to the right, and choose this new point as the origin, the new origin indicated by O prime, the new x-axis becomes x prime, the y-axis is the same as the previous y-axis, and the z-axis is now a new z-axis, z prime. So x prime, y, and z prime define positions within this unit cell, and O prime is the new origin. And you choose the same plane that was asked in the original question. You look at where this plane intersects the x, y, and z axes, and you see immediately that the x prime axis is not intersected by this plane, it is parallel to the x prime axis. It intersects the z prime axis at 1 over 2 times c, so 1 over 2 times this length here, and it intersects the y-axis at -1 times b. So the parameters are infinity, here indicating that there is no intersection between the plane of interest and the x prime axis. So assuming sort of mathematically incorrectly that they intersect at infinity because they're parallel. -1, because along the y-axis you have -1 times b, and 1 over 2 because along the z prime axis you have 1 over 2 times c. So you have the indices infinity, -1, and 1 over 2. You take the reciprocals because that's the rule. And again, mathematically incorrectly, but bear with us, you get 0 as a value for the first one. -1 over 1 equals -1. And 1 over 2 over 1 gives you, or let's say reciprocal of 1 over 2 gives you 2. So you now have these values. You check in step 4 whether you have a reduction necessary to get the smallest set of integers, and you see that you can't get a smaller set of integers than these. What this means is, for example, if you had 0, 2, and 4, the smallest set of integers would be 0, 1, and 2. But here you have 0, -1, and 2, and these can't be made any smaller. So then the integers are as reduced as they can be, hence the crystallographic plane is described as the 0, -1, 2 plane. Again, here there is a problem caused by, I don't know why it's not working. Okay, so there's a problem caused this time by Microsoft Word, and this is the correct version. So what this shows is that the crystallographic plane is the 0, -1, 2 plane. Now, you could look at this value directly. On the exam, you'll be asked to look at this name of a plane and then draw the plane. So then to be able to do that will be a little trickier because you'll have to do the opposite of the formal set of rules given on the previous slide. But you can find a few tricks. One of them is that if you have a zero index value for one of the axes, in this case the x-axis, that means you are parallel to the x-axis, or in this case you are passing through more than one point along the x-axis. -1 indicates that you cut the y-axis in the negative side of the axis, and 2 indicates that you cut the z-axis at the reciprocal of this. So then you should be able to guess that this is the plane that has this name, and then you can go back and check using the known method, the given method, to verify that this is actually the solution. It's a little trickier going in reverse, but it's possible. So here, you show a few different planes. Let's start with this plane, the 1, 1, 1 plane, and this is a common plane. You notice that here you have x, y, and z, and this is the origin. And you see that this shaded triangle, which is the portion of the two-dimensionally infinite crystal plane within the unit cell, within this unit cell, is the 1, 1, 1 plane. And the reason for that is because it doesn't cut the origin, it doesn't go through the origin. It cuts the x, y, and z axes at 1 times a, 1 times b, and 1 times c. Hence, it has the numbers 1, 1, 1. You take the reciprocals, they're 1, 1, 1, and they're the smallest set of integers, hence they're done, and this is the the 1, 1, 1 plane. Now you notice that if you move to the next unit cell, or the next unit cell, these, within that unit cell, this is the 1, 1, 1 plane, and within this unit cell, this is the 1, 1, 1 plane. So then you can imagine that for this origin, although this plane and this plane are not the same, they're not made up of the same atoms, they are parallel, and because they are parallel, they are identical, hence they all get the name 1, 1, 1. And this graph describes why it is okay to either shift the origin or to shift the plane by 1 unit cell length or 2 unit cell lengths in this direction or the other direction, and still be able to get the naming right. So you see here the same thing described a little differently. You see that for this origin, in this x, y, and z, this plane cuts the x-axis and the y-axis at more than 1 point, and it cuts the z-axis at the origin. Because it passes through the origin, you need to shift it. So you could shift it here, or you could shift it here. And in both cases, they would have the name 0, 1, 1 for the plane, because the fact that the bottom of this unit cell, the bottom face, is identical to the top face, or is the same plane as the top face of this unit cell here. This says that all parallel faces, all top and bottom faces, are identical. So this is the top face of this unit cell, or it is the bottom face of the unit cell above it. And because of that, because they're the same face, the top and bottom faces of these unit cells must be identical. Hence, they get the same name, and in this case, the name is 0, 0, 1. So in this case, you see the same thing for a different set of planes. It passes through x equals 1, y equals 1, and it doesn't pass through z. So 0, 0, infinity. You take the reciprocal, it is 0, 0, 1, let's correct that, 1, 1, infinity. Take the reciprocals, it's 1, 1, 0. Hence, it is the 1, 1, 0 plane. This is the 1, 1, 0 plane, and this is the 1, 1, 0 plane. You get the idea that this blue plane, or blue shaded portion of the plane, is parallel to this, and so this is like a stack of papers, and this is like a stack of papers, and all the papers are the same, although they're different stacks of atoms. They're different planes of atoms. They're identical, but in this direction, the spacing of the atoms, hence the properties, are different. Hence, the direction perpendicular to the stack of papers is going to be different. So this shows you the various planes defined within the shaded red within the unit cell. So we stop here and we see that this is a simpler one. So this is the plane called 1, 1, 0 because it cuts through 1, 1 and does not cut z. It's the same as the same plane that we showed on the previous slide. Notice that because it cuts through the corners and is parallel to an axis at a certain, to one of the axes, it has a very simple name. But when you continue and you start cutting through not the corner, but some other point along an edge, you tend to get a slightly different naming scheme. Again, there is a logic to this. The fact that 3 is 1.5 times 2 indicates to us that the intercept along the y-axis is going to be 2/3 of the intercept along the x-axis. And when you actually continue this plane along the x-axis, it would cut around here at 1.5 times a, the distance along, the length along the x-axis. So there is, again, some logic. but it might be harder to follow when you go to, say, this plane. Well, this plane is not so difficult, but this plane is pretty ugly. It's ugly in the sense that, first, it tells you that not all planes are the portions of planes within a unit cell, hence the shaded colored portions, are not always rectangles, squares, or triangles. They may be different shapes, and in this case, it's a trapezoid. And if you continue this plane, because this plane starts at y equals 1, and here it intercepts the y-axis at y equals 1 over 2, when you continue it, it will go one whole unit cell length to x equals 2 as the intercept. So if you can't see this, you'll have to sort of work on it to try to figure this out. So this plane within a given unit cell may or may not be of any significance, but it is a plane that we can give a name to. In fact, you will see that planes of atoms along the faces or along the diagonals are generally more critical than planes of atoms at along any random in any random orientation. Okay. So then, similar to a family of directions, you have what's called a family of planes, and non-parallel planes with similarities, meaning equivalence, meaning number of atoms per area of the plane within the unit cell, can be identical. And here you see three different planes: the 0, 0, 1 plane, the 0, 1, 0 plane, and the 1, 0, 0 plane. And their negatives, or the planes that are similar to them but have a negative index inside them, also tend to be equivalent. And because of that, they become a family of planes, and they get these squiggly brackets. So this is the way of, so when you see this, you understand that it is different than this, in that this is a plane and this is a family of planes. This is an individual plane. And this is some indication of a family of different individual planes. So now we had said that the number of atoms along a direction, or the number of atoms within a plane that fall within the plane, is of importance. So similar to atomic packing factor that we described in the previous set of slides, here we can describe a concept of density, but in one dimension, because it is along a direction or it is along a line. So when planes are slipping over each other, like the individual pieces of paper in a stack of papers, it is observed, like in the stack of papers, that slipping or movement or deformation or shape change of the material, the crystalline material, takes place along the direction where the atoms are packed, or they come together the closest, and they're packed in the densest fashion. So in the case of the stack of papers, the planes of atoms within the pieces of papers are denser, meaning they have more atoms per area, unit area, than in any other direction chosen, say, perpendicular to this. The reason for that is because the spacing between one piece of paper and the next piece of paper is small, but it is much greater than the spacing between individual atoms in a piece of paper. So the atoms are, the structure is a layered structure, kind of like graphite that we'd shown an example of in the earlier set of slides, where the density is greater along these layers rather than perpendicular to these layers. So the linear density of a crystal direction that is shown with the square brackets, HKL being some random, the general naming for the particular indices, is shown with this symbol, and it's described as the number of atoms per length. Notice that this is the same as density in real life, or in larger life, where you have mass divided by volume. Here it's one-dimensional, so in the denominator you have length, and in the numerator you have number of atoms. You could very well define this with mass, but here the beauty is that by ignoring mass, this here applies to different types of materials that use different elements. So here, a density of a particular crystal will be describable by this formula, regardless of what actual element its atoms are made of. So similarly, planar density is described as number of atoms in a plane divided by area. Now you might say that a plane, I said a plane is two-dimensionally infinite, and that is true. But to be able to count the number of atoms, you have to choose an area of interest. So here it should say a chosen area, or the unit area. So if you choose the area within a unit cell, so the shaded area of the plane, then the number of atoms in that shaded area will be of interest. So we choose the FCC unit cell as an example. This is the FCC unit cell, a more realistic representation. You have corner atoms and you have face atoms, 6 of the face atoms and 8 of the corner atoms. And the planar density, which we know because the plane is being given because of these soft rounded parentheses, is number of atoms in the plane. So we look at what this plane is, 1, 0, 0. 1, 0, 0 has an intercept at x equals 1 and is parallel to y and z. So it is this front face of the unit cell, or well, it is this front face in this image, the 1, 0, 0 plane, and the number of atoms is 4 corner atoms, 4 times 1 over 4, plus 1 face atom, which is 1 times 1, equals 2. You may say, why don't we count this atom as 1 over 8 like we did for atomic packing factor? And the answer is atomic packing factor was 3-dimensional, but a plane is 2-dimensional. So when you count inside in a plane or inside an area, you have to be counting in 2 dimensions. So when you only look at the projection here, or the face here, you see that you have 1/4 of an atom or a sphere, because the projection of the sphere is a circle, and you get 1/4 of the circle. And here you get a projection of this sphere, and you get 1 full sphere, 1 full circle, sorry. Hence you count this as 1 and this as 1 over 4. So it's because it's 2-dimensional. The area is A times A. Here it says A squared, but this is again a mistake. Many, many mistakes here. I apologize for that, but that's not. Let's see whether we can fix this, but we're fixing this along the way. So, okay. So the area is A times A. We know that this is also A because it's an FCC, it's a cubic structure. So it's 2 atoms per A square area. Here, A is in a length unit, but it's not specified. And if you link A to the radius of the atoms here, you can do so because in this particular example, each atom is the same size and it's the same type. So this is an example of an FCC metal where you have only one type of atom. And you see that a square root of 2 is equal to 4r. 1r plus 2r plus 1r is a square root of 2, the diagonal of the face. Hence, this relationship from the previous slide set, similar, used here and substituted here, gives us a value of 1 over 4r squared for the planar density of this plane. You see that the planar density is a value that depends on the radius of the atoms. So then you may say that if the radius of the atoms changes, the value of the density will change as well because of this dependence. Hence, you could also imagine that if you had a structure, a crystal structure that had an ionic nature, so it had two atoms, two types of atoms, and if you were looking at the planar density, then establishing a relationship between A and R would require that you choose one of the radii to do so. So it wouldn't be as straightforward as the example here, but it would still be possible to describe a unit, a planar density. So for the density of this direction, hence a linear density indicated by the brackets here, you could look at the length, the direction of 1, 0, 0. So for a cubic unit cell, the direction of 1, 0, 0, let's go back to the example in the previous slide. So the direction of 1, 0, 0 would be one movement along the positive x direction and no movement along the y and z direction. So it would be this edge length here, sort of in the background, going from the origin to this point. And you notice, just like described earlier, it would have two atoms, two corner atoms. And if you were to project that, the projection would be like this. So the length of interest, again, some Microsoft Word related problems that we're suffering, that we're having. Well, there's a problem with the position of the with the arrow, two-sided arrow here, but this length from here to here, from center to center of the two corner atoms along 1, 0, 0 direction, would be a distance of a. So the denominator would be a, and the numerator would be 1 over 2 plus 1 over 2. The reason for that would be that along this direction, because the direction is one-dimensional, the projection of an atom onto one dimension would be the diameter. So one diameter would be one atom, and half a diameter would be, or a radius would be 1/2 of an atom. You have two corner atoms, 1/2 contribution from each, you get a numerator of 1, and the value of 1 over a would be the density along this particular direction, the linear density. So here it says planar, but this is an example of linear density. Now, for planar density along the face of 1, 0, 0, the plane 1, 0, 0. So 1, 0, 0, remember, is this front face. And it says, calculate the planar density of the face plane 1, 0, 0 and the linear density along the face diagonal 0, 1, 1. So 0, 1, 1 indicates that you're moving in the plus y and plus z directions, but you're not moving in the x direction because it's 0. So 0, 1, 1, although shown here as such, it actually, saying we're correcting these, would actually have to look like this. Along that front face, so this would be the 0, 1, 1. Oh, lots of mistakes on this set of slides, although I thought I'd looked at them. Okay, let's see whether, okay. So the 0, 1, 1 direction is one movement along the plus y and one movement along the plus z direction and 0 along the x-axis. So on the front face, the 1, 0, 0 plane, this is the correct vector to draw, and this is the correct direction, going in from this side all the way to this side. Again, infinite in one dimension, but we look at the vector within the unit cell of interest. So then we look at the density. We count the number of atoms. Each corner atom has one radius in one dimension, and a face atom has two radii, hence one diameter. So it is 1/2 plus 1 plus 1/2 equals 2 atoms in one dimension, divided by a naught square root of 2, which is this length. So this is the linear density, and the density of the plane is given as 2 over a naught squared, because you have 1/4, 1/4, 1/4, 1, a total of 2 atoms divided by this area. So notice that this is the same as what we'd seen on the earlier slide. And the linear density within a plane is dependent on the direction chosen. So you could say, change the question slightly, and you could say the planar density of the face plane the linear density of some other direction within the face plane 1, 0, 0 would be a different question. So if you were to go ahead and say, change this to 0, 1, 0, so this would mean, instead of this direction here, it would mean the direction here. And this direction would have a value, well, I can't write over this because it's an image, but it would mean that this has a value of 1. Over 2 plus 1/2, and it would be divided by a value of a naught. So then this would be the answer to the question that we've created. So this would be this new plane, this new direction. It would move not in the x direction, not in the y direction, not in the z direction, but 1 times b in the y direction. So it would be 0, 1, 0. And you notice that this would be 1 over a 0 rather than 2 over a square root of 2. So this would be 1 over a 0 times 2 over 1.4. So about 1.5, and this would be times 1. So this density would be greater than this density. And that makes sense because the number of atoms along that direction is greater per unit length than along this direction. And the reason for that is here there's a spacing between the atoms. And here along this diagonal, there is no spacing. So then you could suddenly go back and undo everything. And you could say, without being given this information, you could say, give me the densest direction. Which is the densest, which direction has the densest linear density? And in which case you'd have two answers. One would be this vector, or this direction, and the other would be this vector, because they'd have the same number of atoms per the same length, hence they'd have the same value. And you might imagine that this vector, which is the same direction but only in the opposite direction, so that the negative of the previously shown, the first vector shown, this would also be a direction, a distinct direction. It would need a new name. It would not be 0, 1, 1, but it would be a different, it would have a different name. In fact, so it would also have the same density, and similarly, this direction would have the same density. So all four of those, by observation, all four of those directions would have the same density, linear density, along this plane. So then, if you look at this crystal structure, this FCC structure, and you ask which is the densest plane, then by observation, you'd observe that the face plane here is dense, is the densest, but it's identical to this plane, and this plane, and this plane. So all 6 faces of the unit cell would have the same density. And that makes sense because this plane is parallel to this face plane, hence they need to be identical as a rule. And this is the same as this other plane. So these would be, it would be possible for an FCC or a BCC or a simple cubic structure to identify the densest planes. And as I said, for various reasons, the densest planes are of particular importance. So if you know what the densest planes are and what their densities are, then you can make observations about, you can make estimations about the crystal structure. Okay, so this concludes this set of slides.